Welcome to the class on reinforcement learning. Let us make a short detour and discuss the role of an inductive bias.
So here we have two data points, data point 1, data point 2. They live in one dimension. This is my x-axis, and we are not in a classification task, but in a prediction task where we have a continuous y value. Now, a somewhat weak inductive bias is that we say somehow we know that these data should be fitted with this kind of function which has 5 parameters, w1, w2, w3, w4, w5. So, but we only have 2 data points. Now, what helps is if we know that 3 of the parameters are 0 in this task. This is an example of a strong inductive bias. Now we have 2 data points as before, and we are left with 2 parameters. We can actually fit the curve. We can fit the 2 data points and extract a very nice curve. Another example of a strong inductive bias would be, for some reason we know that W1, W2 and W3 are 0, in which case we are left with W4 times x plus W5, and we can fit with a straight line. A third possibility is that we know that W1, W2 and W5 are 0. What remains are W3 and W4, and so we can fit with this parabolic curve. So each time, by reducing the number of free parameters by extra knowledge, and this extra knowledge is called strong inductive bias, we are able to fit the 2 data points with a nice curve. The question then is, where does this extra knowledge come from? Where does this inductive bias come from? For example, we may know that radioactive decay leads to an exponential function. And that's why we want to fit with w times e to the minus w2x, where x would be the time t. So knowing a physical law, having extra knowledge, gives us the necessary inductive bias. And this law could come from the physics itself, or it could come from the fact that, in fact, even without explicitly knowing the law, before it was discovered, if somebody has already looked at 125 different radioactive decay processes and each time tried to fit with the function with all 5 parameters, that person would have realized that actually it's the first 2 parameters that really matter. And then you can transfer from a first set of many data fits to other novel data fits, which then, for the novel data, you need much fewer data points. Another possibility to implement an inductive bias is to say, well, I only have 2 data points, but I sort of know, for example, for radioactive decay, that the whole thing is very smooth and decaying over time. So out of my data points, I create new data points, one just a little bit lower on the right-hand side, one just a little bit higher on the left-hand side. This is called data augmentation. And this is an inductive bias because I would have to know how to construct these novel additional data points. And if I do this, then of course I can nicely fit with a radioactive decay law here. I could also fit with the straight line. Now, if the true data points, the black data points, come from something else, if these black data points actually come from a flying bullet, which means a parabola, then my data augmentation method that I used before would have been completely wrong. So you really see it's your prior knowledge about what you should expect that allows you to do data augmentation that allows you to use your inductive bias. The wrong inductive bias gives you the wrong thing. So, induction in general is finding a rule, which means a function, from specific examples, and the inductive bias is a prior preference for specific rules, for specific functions. And this can be in a form of an explicit inductive bias. I know that for radioactive decay, it should be an exponential, so the other three parameters must be 0. Or it could be an inductive bias through transfer learning. I first have looked at data fits of many different models of radioactive decays, many different data sets of radioactive decay, and then from that I know what kind of model will work and I will choose the best one for the current case. Or I can bring in an inductive bias, not by choosing a formula, but by appropriate data augmentation. I know that for radioactive decay, neighboring points have similar values, they should go down, and this allows me to construct points. So let's just review these inductive bias notions in the form of a quiz. And I remind you that you can stop the video at any point. So first question, with a strong and correct inductive bias, I can reach a low test error with very little training data. You think that this is correct? And yes, this is correct. Second, with a strong inductive bias, the test error will always be low. Think about this. Is this correct? No, this is not correct. It could be the wrong inductive bias, or it could be the correct and strong inductive bias, but you still don't have enough data. So for a complicated model, you still need a lot of data. Third question, data augmentation is a heuristic method to get more training data. Well, yes, this is correct. In data augmentation, there is an inductive bias in the form of our assumptions about reasonable transformations to be applied to the data. And yes, this is correct. Final statement, choosing a specific neural network architecture is equivalent to choosing an explicit inductive bias. Think about this. And yes, this is correct. And this will be the point of the lecture today. Deep neural networks have been around for a very long time. Convolutional networks can be traced back to the neocognitron of Fukushima in 1982. So the elements of deep learning were around, were available. However, the revolution of big deep neural networks really started in around 2012 when deep convolutional networks were trained on GPUs. So deep networks, deep learning really refers to multi-layer networks, but the breakthrough came on an image recognition task when convolutional networks showed that they were really great. So here is the cross entropy loss. You can also look at the accuracy. It doesn't matter. It's some kind of image recognition task. And if you use just a standard multi-layer deep network, you can look at training and validation error. They will level out here. If you do the same thing with a convolutional network, you are much, much better as indicated here. So it's really the deep convolutional networks that enabled the breakthrough. Okay. So the big success of deep neural networks came when they worked on large image databases. So why are convolutional networks better than other networks on image tasks? And the answer is there's a rather explicit inductive bias in the convolutional structure. What is this bias? Well, the bias is an invariance to a local translation. Here on the table we have a coffee cup, and we want to classify it as a coffee cup, and it remains a coffee cup whether it sits here or whether it stands there. So this translation invariance to shifts of the object is the key idea, and this idea is encoded in the convolutional architecture of the neural network. So convolutional networks are a special case of generic layered neural networks, yet they work much better, and the reason is they have a good inductive bias. And in the following we'll ask, what are good inductive biases for reinforcement learning?